morning. Myself, Shrikant Rao SK, Assistant Professor in the Department of Electronics and Communication Engineering, Vivekananda College of Engineering and Technology, Puttur. Today, in the Advanced Communication Lab, we will study the characteristic of ring resonator. Now, this is a ring resonator. This ring resonator, the construction is microstrip line. The microstrip line, the construction wise, if I take, there is a dielectric material above which the conducting strip is placed. If I take the construction or actual ring resonator, there will be one dielectric, grey color, and there is a conducting strip. So this conducting strip has some width and some height or some thickness. So that I am representing here. So height of the or thickness of the conducting strip, dielectric substrate, conducting strip of width W. Now what I have to do in this experiment is I have to calculate what is the dielectric constant of the ring resonator. So for that, what we need is a microwave source, a variable microwave source which has the starting frequencies from 2.2 to 3 GHz and a VSWR meter. Now what I do is I switch on my source. As I switch on, there are certain initial procedure to be followed. For this, first initial procedure is my RF should be RF power level knob. So this is the RF power level knob, so should be always at minimum position, and I can choose either amplitude modulation or frequency modulation, and RF should be on. So this is the basic requirement for switching the microwave source. So next what I do is from the source with a 3 dB attenuator I directly connect it to VSWR meter. In the VSWR meter I can have two choices. I can select either input 1 or I can select input 2. So in this experiment I am selecting input 1. I switch on the VSWR meter. So you can see the difference now. My select channel is 1, input 1, and all my measurement is normal. Next what I will do is I will increase my RF power level. So if I increase this, and you can see the difference. I am getting the deflection. Now the deflection is my range knob or the range dB knob, it is in 30 dB. The deflection is somewhere around 3. So that means my reference power, it is 33 dB. So the reference power is 33 dB and my frequency is 2.02 GHz. So next what I will do is I will start increasing my frequency, say around 2.1. My reference power is somewhere around 33.5. 2.2 around 35. 2.3 again around 35. 2.4 34.5. 2.5 34. 2.6 again some 34. 2.7 33.2. 2.8 again some 34.1. 2.9 34.5. 3 GHz. So at 3 GHz my reference power is 34 dB. So now you can see the difference. So when I started frequency from 2.2, I went on till 3 GHz. My all reading is around 34-35 dB. So that means there is a minimum attenuation happening from the source to the VSWR meter. So next what I do is I connect my ring resonator. When I connect my ring resonator, you can see the difference. My range knob was in 30. The deflection, it was somewhere around 33, 34, 35. When I connect my ring resonator, the deflection, it went beyond 10. So that means my reading is now, or my reference power is some 30 plus 10, 40 plus. I'll go to next range. Again 40, beyond 10, some 50 plus. Again I'll go to next range, 50. Again beyond 10, some 60 plus. I am getting reading around 60 dB. Now range knob is in 60. The deflection is somewhere around 60. It's around 5. So that means 65. Now what has happened is, after connecting this, or after connecting my ring resonator, a high attenuation has taken place. So why? Because my reference, it was around 33. Now I am getting the reading around 65 or 66. So that means around 30 dB attenuation has taken place. Now what I'll do is, again I'll start frequency from 2.2 and I'll note down all my dB level. So 2.1 or 2, it is 68. 2.1 around 67. 2.2 again around 67. 2.3 again around 67. 2.4 66 or 67. 2.5 is around 55. 2.6 again some 67. 2.7 68. 2.8 again around 68. 2.9, it is 64.2. 3 gigahertz. 68. What you can observe here is, except one frequency, so that is 2.5, at all the other frequency there is high attenuation happening at 2.5. So 2.5, the attenuation is minimum. It is around 55. So that means at this frequency there is a resonance happening. So what happens in the resonance is, attenuation is minimum. If I take the plot of frequency versus attenuation, at one frequency around 2.5 gigahertz there is minimum attenuation, and at all the other frequency there is high attenuation. So this you can observe from VSWR meter reading. So at 2.5 my attenuation is 55, or my reference power, it is 55. At all the other frequency it is around 68, 69. So what I have to do here is, I have to note down this frequency. So this frequency, why? Because this is the resonant frequency. So I'll note down this frequency FR as 2.5 gigahertz. So next what I'll do is, I'll use the equation 2 pi R equal to N into V naught divided by FR into square root of effective dielectric constant. Now why effective dielectric constant? Because my construction, it is microstrip line. When I excite my microstrip line, this electric field, so that will be partially into air, then into dielectric. Because of this, there are two dielectric medium coming into picture. One is the air, other one is the medium or the actual dielectric of the material. Because of that, first what I have to do is I have to calculate the effective dielectric constant. From the effective dielectric constant, I have to calculate the actual dielectric constant of the material. So first what I will do is I will calculate the effective dielectric constant. Effective dielectric constant is nothing but N into V naught divided by 2 pi R into Fr, or effective dielectric constant I will calculate. Now here N, it is the mode, it is 1. V naught, it is the free space velocity, 3 into 10 to the power 8 meter per second. 2 is the constant, pi 3.14. R is the radius of the ring. The radius of this ring, it is 12 mm. I'll substitute this and I'll get effective dielectric constant. Effective dielectric constant will come around 2.86. Now from the effective dielectric constant, I'll calculate the dielectric constant. The dielectric constant is given by this equation, 2 into effective dielectric constant plus 1 plus 10H divided by W to the power minus half minus 1 whole divided by 1 plus 10H divided by W to the power minus half plus 1. So I substitute all the parameters. 2 into the effective dielectric constant 2.86 plus 1 plus 10 into H. Height, and the H is the height of the substrate. Height of the substrate, it is 0.76 mm. That is substitute divided by W. W is the width of the strip. It is 1.84 mm. 1.84 mm whole to the power minus half minus 1 whole divided by 1 plus 10H. H is 0.76 mm divided by W. W is 1.84 mm. So I have substituted all the all the constant, and what I'll get is I'll get the dielectric constant of the material as 3.02. So that is nothing but the dielectric constant of this grey material.